All right, we are now recording. Ask the other two, but Molly, any issues, concerns, problems need to be addressed?
No, sir.
All right, good deal. Okay, I thought maybe someone else was coming in because my toolbar lit up, but nope, still just the three of us. All right, well, where we left off last time, we're still in Chapter 8 and should finish it tonight. Chapter 8 is work and energy, and we're definitely in the energy part now. The work part was the first part. I think the section that we're in is conservation of mechanical energy. And I believe where we begin tonight is in example 1, which is before the slide that we are now. So maybe I should go back one slide. Let me just see if it will go back a slide. For some reason it won't until I click on the screen, and then it will. Okay. So, let me go to the whiteboard, and we will move from there. Okay, here's the whiteboard. Now, I need to move this toolbar, taskbar, whatever you call it, out of the way. They put it right down in the middle where it interferes with everything. And at the same time, I'm going to move my whiteboard ever so slightly. So try to get it so I can get maximum writing room. Okay, that's just about it. Okay, if there are no issues or concerns, example 1 on page 220. And I told you what it was. It's section 8.4, conservation of mechanical energy. Example 1 on page 220. A pile driver falls freely from a height of 3.50 meters above a pile. So that's our H. Used to call it S, now they're calling it H. This means it's not a horizontal direction. It is a vertical direction, and that height is 3.50 meters. Okay. I have to stop and look to make sure no one's coming on. This window that keeps phasing in and out usually blocks somebody, but I'm trying to make sure it doesn't. Okay. A pile driver falls freely from a height of 3.50 meters above a pile. What is its velocity as it hits the pile? Wow, they give us one piece of information and they want us to calculate velocity from that. Okay, that's the unknown here. Where they're counting on us using the formula we hit right before we left on Tuesday evening. And I'll write that formula down for you. Well, might as well write it right here. V is equal to, now this is when you have a free fall situation that your thing is coming down. We're assuming no friction, no air resistance, nothing else is interfering. We're saying the potential energy at the top before it's released is equal to the kinetic energy at the bottom when it hits, and that then gives us this formula. Kinetic energy, 1/2 mass times velocity squared. The potential energy at the top, gravitational potential energy, mgh. The m's cancel out, and then you have V is equal to, and here's the formula they got, bottom of page 219, V is equal to the square root, that's an ugly square root symbol, of 2gh. And believe it or not, that's all there is to it. Okay? Now, what they didn't give us, but they're assuming you know, is what in the world is G? Anyone know? And that's a pretty ugly square root symbol again. 2 times, what's G? Anybody?
Gravity.
The acceleration due to gravity, which is 9.80 meters per second squared. Okay? Times H, which is your 3.50 meters. My pen's not writing well. Okay? I'm not writing well. Okay? There's the formula. Grab your cell phone, calculator, whatever you're using. I happen to be using my cell phone. Okay, and since this is going to require a square root, I'm going to turn it sideways so you can get the square root. And in this cell phone, I don't know how yours is, you enter the argument first and then you do the square root function. So I enter 2 times, now if you got a graphing calculator or any kind of calculator, most of the newer ones you do the square root symbol first. Not this one. This is a telephone. It has to do it the old way. 2 times 9.8, you don't have to put that extra 0 on it. The cell phone will take care of that. Times 3.5 equal, okay, and then take a square root. Now the square root symbol, if you're not familiar with square roots, is that symbol right there. And you see the index of 2, that means the square root. I think this one has an index of 3, that means a cube root. This has an index of y, meaning you're taking the y-th root. Okay? So I'm going to press the square root symbol. I'm going to try to push the correct. All right, and there we get a big long number. What do we use? Okay? You use count off 3 digits because you got 3 digits here, 3 digits here. So that's going to be, did anyone get it?
I got 8.28.
Okay, 8.2. And the other third digit is an 8, but you look to its right, and that's a 2. So therefore, yeah, we'll leave the 8 alone and drop the rest. If that was 5 or more, we'd have bumped that up to become a 9. Now we have to figure out what units we do. That's the square root of that number that we had. But the units are meters times meters, that's meters squared per second squared. But you take the square root of the units as well, and that would be meters per second, which is a fantastic unit for velocity or speed, meters per second. And that's what the question asked. Okay, it said, with what is its velocity as it hits the pile? And they got 8.28 meters per second squared, meters per second. Perfect. Now, that's just one example of many examples we could have of conservation of energy. Another really, what you might say, popular or useful one, let me clear my calculator. We don't need that anymore. I've got it upside down. Okay. Now, another common example of this is what we have on the slide that I just covered, and that will be this one. Sorry about that. Sorry. All right, here's someone coming in. It looks like Manessa. If I can find my cursor, I'll admit Manessa. All right, so welcome, Manessa. We just finished doing example 1 at the top of page 220, chapter 8, work and energy. We're in the energy part, 8.4, conservation of mechanical energy. and we're getting ready to do the bottom half of the page, which begins pretty much with, if I can get with this figure. Now, I have a few problems with this figure, not with the concept of the figure, but with the actual, some of the things they have written on it. And that is the angle of 65 degrees. We're not going to be using the angle, so don't sweat it. You don't have to know trick. But it's still, I think, not a good thing to put there. And here's why. We're not going to derive how they got this calculation, but I'll tell you this. This calculation that we're going to be using here is basically good for small angles, okay? 65 degrees is not a small angle, so kind of ignore that part of it. Not that we're using that by any means, but this is, they're using it as an illustration, not the best illustration, okay? Now, what they're trying to say here is you can have a pendulum. Now, I don't know if you know what a pendulum is. Picture a grandfather clock or a grandmother clock, a clock that has one of those things that swings back and forth. That's the pendulum, okay? And what the deal is here, now this one looks like a wrecking ball, which it could be as well, okay? If you pull that wrecking ball or the pendulum off to the side here, what you're doing by lifting it up like that, you're taking it from what its zero reference level is, as low as that ball could possibly go, which would be down here somewhere, to a height that's over here. And when you do that, you're giving it gravitational potential energy because you're increasing its height above its zero reference level. MGH, that's your gravitational potential energy. And when you hold it there and stop it there, all of its energy is gravitational potential. It's not moving, so it has no kinetic energy. That's why kinetic energy here, when that fades away, you'll see, is basically zero. It's not moving. All of its mechanical energy is potential energy, gravitational potential energy. Now, when you release it from rest, then it starts falling, of course. When it starts falling, it gradually is picking up kinetic energy, all the same time losing its gravitational potential energy. Okay? So, that's what happens when you release it. There, it's halfway down. You had it up here, now it's about here. It's lost half of its potential energy because it's halfway to what we consider its zero reference level down here. So therefore, it only has half the potential energy it had, but that energy didn't go anywhere. It just changed to kinetic energy. Now, half of that energy is gravitational potential. The other half is kinetic. Okay? Because as soon as you released it, it started picking up speed. When it started picking up speed, it started picking up kinetic energy while it was losing its gravitational potential energy. Okay? In a little while, it will reach the lowest point that it can go. And at that point, it doesn't have any more gravitational potential energy because that's as low as it can go in this problem. The rod here, or the string, the wire, whatever is holding it up, is keeping it from going any further. So its gravitational potential energy at this point is as low as it can go. We'll count that zero. And as soon as that box fades away, you'll see that's true, if the box will ever fade away. Fade away, box. We don't want you here. Okay, there it goes. Now I need my cursor back. It's coming, but not here yet. There it is. Well, it's not going to show up until the box comes back. But it's a zero potential energy here and maximum kinetic energy here at the bottom, because that is as low as it can go. All of its mechanical energy is now resident in its kinetic energy. The potential energy is 0, because that's as low as it can go in this problem. So the potential energy went to 0, or awfully close to 0. All the mechanical energy is now kinetic energy. Now, in reality, that's the fastest that it's moving, because once it moves past here, it starts going up again. And as soon as it starts going up, it's gaining gravitational potential energy, but losing kinetic energy. You don't ever completely destroy or create energy. You just change its form. Okay? So as it moves up from here, it loses kinetic energy while it's gaining gravitational potential energy 1 to 1. Okay? And when it got back approximately, where did the cursor go? Approximately here, it would be half and half. And when it moved back to here, guess what? It can't go any higher than here because that's the level that it started at. If it went any higher, it would now have more potential energy, gravitational potential energy, than it did to begin with. But at the beginning, that was all gravitational potential energy. Now you might say, is there no way to make it go higher? Yes, there is. If rather than releasing this from rest, which is what we said, you just dropped it and it started falling, if you threw it, then you're giving it an initial velocity. That initial velocity would be kinetic energy that it didn't have when you released it from rest. So therefore, you could get it. Then it would go higher on this side because you have not just kinetic potential energy here. When you threw it or pushed on it or launched it, you gave it some additional kinetic energy. So it would then go higher on this side. How high depends on how much energy you gave it, how fast you pushed it. Okay? We're assuming you're releasing it from rest, so that means you can't go any higher than the initial position. Okay? And that's what this slide shows. You went from maximum gravitational potential, 0 kinetic, to about 50-50, to all kinetic, 0 gravitational potential, back to around 50-50, and then back up here, and now it's all gravitational potential energy. No kinetic energy, because if it had none here, it won't have any here because the gravitational potential is the same at both levels. So whatever the kinetic was here has to be the same here. Excuse me just a second. Sorry. I've had scratchy throat all day today, so a little bit of carbonation seems to help. Any question about kinetic and potential energy changes in the pendulum as it goes back and forth? The total energy is the mechanical energy. It does not change. And remember from last time, mechanical energy is the sum of potential energy plus kinetic energy. Any potential energy. So far in this problem, we're only using gravitational potential. All right. That leads us to example 2, which is not a pendulum problem. They do not do a problem with the pendulum. Not going to say they didn't at the back of the book, but we'll see. But in the text, they're not doing an example with pendulum. What they do an example with, and this is pretty hairy, okay? It is a series of issues. And this is a huge table. That's the table. And let me see if I can pull it far enough back for you to see the whole problem. There's the whole problem. It's hard to read, I'm sure, from there, so I'll read it to you. I don't believe they have this on the slide set. No, they don't. Okay? So, let's go to the whiteboard. Still only... Oh, wait. Here's someone coming in. I can't see who it is. I'm going to have to admit them, but I could not see it. Blacked them out completely. Who was that was coming in? Are they here yet? Could y'all see a name? Okay, what I can do is... Okay. It's Mika. All right, Mika's here.
Hey.
Hey. All right. We got Jalen, Macy, Mika, Manasseh, and Molly. Jalen, you're the odd man out there, only non-M name. What is going on here? You and I, in fact. Okay. So, glad you're here. Now, let's go to the whiteboard. By the way, Mika, we're on page 221, example 2 in section 8.4, conservation of mechanical energy. This is a huge, huge problem, okay? Not a hard problem, but just a big problem, okay? I'm going to clear the drawing. That was left over from example 1. Here's example 2. Here's the deal. You're dropping a 5-kilogram mass. Now look how many decimals they have there. 3 zeros with the 5, that makes 4 significant digits. A 5-kilogram mass from a hot air balloon, so that's way up there in the sky, 400 meters above the ground. 400 meters above the ground, dropping a 5-kilogram mass from there. Okay? What they're asking you to do is find the kinetic energy, its gravitational potential energy, the sum of the kinetic energy and gravitational potential energy, that would be mechanical energy, in 1-second intervals until the mass hits the ground. Now here's the assumption, no air resistance. Now, again, definitely not a true assumption, okay, but a working assumption. And here's why I say not true. There's always some air resistance, but as long as your velocity is pretty small, it's negligible. So you might say, hey, that's okay then. Except 400 meters is way, way, way up there. If you think about this, this room that I'm in now is about 3 meters tall, okay? So it would take approximately a 3-story building to make a 10-meter drop, okay? This is 400 meters. So that's 40 times 3. That would be a 120-story building, okay? 120 stories up there. That's way up there. That's taller than the tallest tree we have in our backyard. And we have some big old trees in our backyard. That's way, way up there. And when you're falling from that distance, you're going to pick up enough speed. In reality, you probably are going to have some air resistance. But we're ignoring it for this problem, okay? Assume no air resistance. So what you do, they have this table. And I sure don't want to fill in the table. And I'm hoping all 4 of you have books. Or is it 5 of you now? I think it's up to 5. Yeah, 5 of you have books. So if you look at the table, here's what you're doing. Okay? The first column is your time. So at 0 seconds, you're way up there. Okay? Now, column 1 lists the time in seconds, and you're going to do 1-second increments. So you could fill up all of table 1, except you wouldn't know how far to go. So let's just do them one at a time. At 0 seconds, you're up at the top. How far are you? Okay, what the second column is, column 2, is the distance the mass has fallen from the balloon. Okay, so you dropped it from the balloon, how far has it fallen? With 0 seconds, you haven't released it yet. So it's fallen 0 meters. Now that symbol we're using S, that's the old distance formula symbol that we used before S. Now, in the future, after you release it, that S is exactly 1/2 gt squared. Because remember, your acceleration times your time squared, 1/2 the acceleration due to gravity times the time squared is how far it fell. It's not how far it is above the ground, how far it fell from the hot air balloon. So that's how we get S. Okay? And here comes Devin. That time the black box didn't block him out. So Devin Verdell is here. Welcome, Devin. Okay, we're up to 6 students. One more, and we've got all the ones that have shown up this term. Okay, don't know whatever happened to Valencia Bell or Christopher Nicholas Nees, but we haven't seen either one of them all term. Miss Bell never paid for the course, so I guess she assumed she's not going to take it. But Mr. Nees did pay for the course, but he's never been here, so I had to report him as a no-show, which means I'll probably take him out of the class. Okay, so let's get back to the problem. Devin, we're on page 221, chapter 8, Work and Energy. It's section 8.4, Conservation of Mechanical Energy. Example 2, what we have is a 5 kilogram mass way up in a hot air balloon 400 meters above the ground. You're going to release it from rest. Not throw it, release it from rest. Okay? But at time 0, you haven't released it yet. So how far has it fallen? 0. It hasn't fallen any. You're still holding on to it. Okay? Now, what's its velocity? 0. You're still holding on to it. It hasn't started falling yet. What's its kinetic energy? 0, because it has no velocity. Velocity is 1/2 mv squared. Okay. So what's its height above the ground? 400 meters. That's the, it's how high the hot air balloon is. It's in the hot air balloon. It hasn't fallen any, so it's 400 minus 0, which is 400 meters. So what is its potential, gravitational potential energy? That would be mgh. M is 5 kilograms. G is acceleration due to gravity. Since we're in the SI system, that's going to be 9.80 meters per second squared, and its height 400 meters. Okay, so multiply those together, you get 19,600 joules. Now here's the thing that's a little squirrely here. They're saying that first 0 is significant. The 1, the 9, the 6, and the first 0. Okay? I think that's probably inconsistent with what they've been doing, and here's why. Because your G was only given to 3 digits, 9.80. Okay? So if that's only 3 digits, you can't get 4 digits out of it. So I would have rounded that 19600. Neither one of the zeros being dependent. That's your potential energy. And since your kinetic energy is 0, your mechanical energy, or they're calling it total, I would call it mechanical energy, is 19,600. Okay. Now, at time t equals 0, you release it from rest. You don't throw it, you release it from rest. Okay? It starts to fall. And you use for S 1/2 gt squared. So you're 1 second later, so that's 1 second squared is 1 square second times g is 9.8, and half of that would be actually 4.9 times 1. So you're 4.9 meters is how far it fell. Okay? What was its velocity? Well, the velocity, column 3, what we did earlier, the square root of 2g. Now they put h here, but in reality it's s, how far it fell from the top. Not h, how far it is from the bottom, how far it fell from the top. So that would be square root of 2 times g, which is 9.80, times how far it fell, and that we just calculated 4.9. So let's do that calculation here just to see if they got it right. Okay? All right. Or what? There it is. It's got to turn it sideways so we can use the square root key. It's square root of 2GH. So it's 2 times 9.80 technically, but the calculator doesn't care, times, and how far did it fall? 4.9 meters. Hit an equal sign and take a square root. And we get 9.8, actually 9.80 meters per second. That's this velocity. So now it's moving, 9.8 meters per second. What is its kinetic energy? 1/2 mass, we'll get the mass in a minute, times this velocity squared. So the first thing I'm going to do is square the velocity. If you see on my calculator here, the key right there, I think, is a x squared key. Yeah. So I'm going to square that velocity. That's what we had just a few minutes ago. Times 0.5, that's 1/2. I could have divided by 2, I should have. Times the mass, which is 5. Okay? Equal 240.1. I would have said 240, that's what they did. 240 joules. Okay? That gave you your E sub K, kinetic energy. H is simply 400 minus your S. The 400 was how high you were in the balloon. It fell 4.9 meters, so that means it's 395.1. There's your H. The potential energy, gravitational potential energy, is just decreased slightly, so that's mgh. M was 5 times 9.8 times that number there, 395.1. That gives you 19,359.9. It's awfully close to 19,360, but not quite. Okay? No, not quite. 19,360. It was before 19,600, so it lost some potential energy, but add the potential energy to the kinetic energy and you still get 19,600. Okay? And you just keep going that way. After 2 seconds, you've fallen further, 1/2 GT squared. Now it would be 1/2 9.8 times 4, because 2 seconds squared with the 4, that gave you 19.6 meters it's fallen. Its velocity is the square root of 2GH. Do that again with the, now it's S. You use the S, not the H. And that gives you, gone up to 29.4. Square that, multiply it by 1/2 the mass, you could just say 2.5, and you get now the kinetic energy is up to 2,160 joules. Your H is decreased because your S increased, so your H is 400 minus 44.1, I believe it was. Whatever, yeah, I've lost where we are in the thing. But that's all you do. You just use the formulas time after time after time again. And what you see is happening here, I'll try to point this out to you. Okay? You see what's happening as it falls. The distance that it's fallen is increasing, which means the velocity is increasing, which means the kinetic energy is increasing. Well, if the distance it's fallen is increasing, that's the distance that is above the ground is decreasing. And if the distance above the ground is decreasing, that means the potential, gravitational potential energy is decreasing. But guess what? For the same amount that the kinetic energy went up, gravitational potential energy is going down. and you wind up with the same mechanical energy. Mechanical energy is conserved. Okay? That's what they're getting. And that was the name of this section, the conservation of mechanical energy. Any questions on that? You can work through that table as much or as little as you want to, but that's that example. Now, the rest of the chapter is pretty much just conceptual. So let me get out. I went to okay, we got 6 people here. Yeah. Okay. Let's go back to the PowerPoints. And here's the one that's the top of page 222. Okay, figure 18.5. Let's talk about what is happening. Okay, I'm not a big roller coaster fan. Some of you may be. If you've ever been on a roller coaster, you know something pulls you. There's a hook over under the car or something pulls you as high as you're going to go on that run. That's the point P here. Work is done to take the roller coaster car from the beginning of the ride, which is down here, to the top of the structure here. That's whatever your setup is, whatever is pulling you up there, that's work being done. What is the amount of work? mgh. The mass of that car, you and everybody else in it, times the acceleration due to gravity, times your height above that zero reference level. That's where you, as low as you can go on that track, that's your zero reference level. Okay? So work is done to get you there. That's giving energy to the system. Okay? It's giving potential energy to the system because it's moving up there slowly, gradually. Now, as soon as it gets there and you leave, it leaves the peak of the ride, in other words, that's the P here, the highest point, the sum of the potential energy and its kinetic energy is equal at every point on the ride, at least theoretically, okay? In other words, the mechanical energy is conserved because the sum of potential energy plus kinetic energy is mechanical energy, and that is constant. Now, what happens? You get down here around Q, and it looks like you drop maybe 2/3 of the way down. So that means your potential energy has decreased to about 1/3. But what you lost in potential energy, you gained in kinetic energy because this car is flying down here now. Okay? And then it goes past here and goes to point R. Now, point R is basically about the same place you left it, probably a little higher. And then it goes up, and when it goes up here, it's slowing down because it's gaining gravitational potential energy again. Now, when it gets here, it's still moving. Why? Because it's not as high as it was before. There's still some kinetic energy in it. And then it increases again, kinetic energy. As it falls, it dips and changes its direction again and starts decreasing again. Okay, comes again and ultimately goes past here. Now, if they stop the ride there, you're done. That's your zero reference level. However, if you go a second time, supposedly you'll get all the way back up to where you were before. Supposedly. Why do I say it that way? Because there's always friction. If you can hear that roller coaster on the track going, or whatever sound it's making, not the people screaming, but the noise of the roller coaster on the rail. Okay, when it goes down to the bottom here and goes up, you might hear some squeaking. Certainly when it goes around a tight bend, you'll hear some squeaking. Anytime you hear noise caused by that, that means you're losing energy to make the sound. Now, if it's all incredibly well lubricated, so there's absolutely no friction loss, you still got air resistance. because there's air here, it's falling. Now they've made it somewhat aerodynamic, trying to minimize that, but guess what? There's always some air resistance. So in reality, it's not going to make its way to the top unless this. Up here at P, you didn't let it fall from rest, you pushed it. So let's say that same hanger here that got you here gives you a shove. In other words, it yanks you down, okay? Then that gives you more kinetic energy. So now all the energy up here isn't gravitational potential, it's gravitational and kinetic. And that allows you to lose a little bit of energy through your pins, through your turns, through everything else, and then maybe you can make it back up here. But you're not going to be able to do it indefinitely because every run you're going to lose a little more. At some point, you wouldn't be able to get it back. In reality, they're going to put on the brakes here and stop you, okay? And let the next paying customers come aboard. All right, so that's what we have with conservation of mechanical energy with a roller coaster. As long as there's no friction, no air resistance, it'll keep going forever. You know, in reality, it won't. There's always friction. There's always air resistance. Okay. Now, this is in a later problem. What I'm going to point out to you now is a concept. And you don't have to do any problems with it, but let me just give you the concept. There are a couple of kinds of collisions. One kind of collision is called an elastic collision. That means when two things collide, they bounce off with no loss of energy. Okay? If they were to collide and then stick together, they've obviously lost some energy. That would be a totally inelastic collision. They did not bounce off freely. Okay. So those are the extremes. A totally elastic collision, they bounce and don't lose any energy at all. An inelastic collision, they collide and basically come to a stop or move slightly slowly in one direction or another, obviously losing energy. Okay? And then in between you have inelastic collisions, but not totally inelastic. Okay? Now, I want to say this, and it may not sound fair, but there's very few totally elastic collisions. About the closest you ever get is, I don't know if you've ever seen an air hockey table. So you have these little blowers, holes that air is blowing out, so the puck never really sits on the table. It rides on a cushion of air. There's still a little bit of resistance, but not very much. And those collisions then are going to be very close to inelastic or elastic collisions. Another one is when the collision is actually not quite a collision. Say if you had two magnets, a north magnet here and a north magnet here, and as they come closer, the magnetic fields keep them from touching and push away, especially if on the air hockey table you'll have almost no resistance there at all. That would be as close to elastic collisions as you actually get. Okay? Maybe some elemental particles colliding and stuff, you might get elastic collisions. Okay? But that's all they do with it, and you don't need to go any deeper into it. Now, there's a little try this activity called backyard physics. I don't know if anyone ever plays croquet anymore. I think we have a croquet set in our garage that I don't remember where we got it, when we got it, why we got it. I think maybe my wife got it from her parents because no one used it there. It's sat in our garage ever since we've had it. We thought a few times when kids came to visit, we'd set up the wickets and let them play. No one's ever wanted to play. It's an old game. The British like it, I think, a lot more than Americans do. Maybe up in the Northeast they still do it. I don't know. But anyway, it shows conservation of It's not quite conservation mechanical energy because it's played on the grass. You know there's air resistance. I mean, there's friction loss. Now, another physics connection here is landing on an aircraft carrier. And they don't have a figure of this, but they have a picture on the next page. Okay? And how you land on such a short thing is they have a hook. They have a steel cable running across the deck, and the pilot comes down with a hook dragging behind them. It grabs the table, and it yanks you to a stop. Okay? How you take off from such a short landing airstrip, they have a catapult that throws you off. This was a jet. The jet would be at full throttle before it did, and then it throws you off the end. You get enough speed. You still drop a little bit, but it's high enough off the water, not that high, but then the jet engine takes you on up. I've been on an aircraft carrier. I had one launch and one recovery. I wasn't the pilot. I was a passenger, and it was a small plane, a prop plane, but they did throw us off with a catapult, and it caught the hook, when we came back down. Actually, it was one landing and then one takeoff. Left from Grant Land and took off on a regular strip, went out to sea, landed on an aircraft carrier, did what we needed to do there, and then they launched us back off. So I have done it. It's quite an acceleration. That's almost the end of the chapter. There's just one more slide. We haven't gotten there yet, but we did finish 8.4. Homework exercises 8.4. Any of the odd number exercises 1 through 13 on page 224. Okay? Now, moving on to 8.5, alternative energy sources. Now, this is all verbiage, no problems. Okay? And rather than write it down, what do we mean by alternative sources? So far, most of what we do has been burning fossil fuels. It's not always been the case, but it's been the case for most of our lifetimes anyway. What we're trying to do now is get away to alternative fuels so we don't pollute the air as much, we don't use up the fossil fuels at the rate we've been using them, and it's better environmentally, it's better energy conservation-wise, it's better just about every way. They mention a few of these. Now, during our lifetimes, before I was born, they already had hydroelectric plants, and they still have them. Okay? That's when they build these dams on rivers, and you have to do it where there's a pretty good fall off. Okay? That would be mostly in northern Alabama, though there are a few south of us, but not very many very far south. Once you get below Montgomery, you won't see any more hydroelectric dams, I don't think. Not many anyway. Above Montgomery, you have a few. I think Lake Martin is somewhere in there. Logan Martin is east of here. Smith Lake is above here. Gunnersville. There's lots of them. Lay Lake. These are all, I don't know if they're all hydroelectric, but they're mostly man-made lakes. Okay? I'm guessing they're probably hydroelectric. So what you use, you build up water behind the dam, giving it greater potential energy, gravitational potential energy. You let it fall through the sluices of the dam, and at the bottom it's gained a lot of kinetic energy. That kinetic energy is used to turn turbines, which are electrical generators. That produces electrical energy. That energy is then sent to the homes. Now, back when we did the big building boom of hydroelectric dams, that was back before a lot of these areas up north of here were very well populated. Winston County is mostly has a lot of Smith Lake in it. It was a very poor county, and they didn't have to move very many people. They didn't have to pay them very much money as they buried their land underwater. Okay? Nowadays, to build another dam, People live all over rivers and lakes and stuff. Nobody wants their property done. We have used most of the usable places for hydroelectric dams. So therefore, back in the day, we probably were manufacturing a large percentage of our energy with electrical energy anyway. However, as we get hungrier and hungrier for fuel, we haven't been able to build any more dams, so more and more of our energy comes from fossil fuels, from gas, coal, fuel, anything else. So hydroelectric, even though it's it's expensive to build the dams, but then it's cheaper to run the turbines, okay? Because you're using nature, you're using gravity to run. However, it only manufactures about 3% of our electrical energy and not going to grow very much at all. Now, something that has been growing of late is wind energy. And you can see in this picture, there's a whole bunch of these windmills. They are very sleek, modern windmills. At the top there, that little black thing in the center of those three blades, that's your electrical generator, okay? So every one of them is generating electricity. And look at all those in the background there. They're generating electricity, all going into a common grid. Now, of course, they only work when there's wind. And some places in the U.S., though, have almost constant wind. If you've ever been in San Francisco, you know the wind is always blowing. Chicago is called the Windy City, okay? Most of the West Coast, wind coming off the Pacific is very, very regular and fairly strong. So all up and down the West Coast, you have these wind farms. Not in high population areas, but in other places. My wife and I, she had professional meetings in Salt Lake City one summer. It was the week in between our summer and fall terms. So I got to go with her. We left early and drove around and saw some of the area, some that we had seen before, some that we hadn't. We drove from where we landed in Salt Lake City. We drove up into Idaho. We had been into Idaho before, but we drove a little bit further. Then we crossed over into I want to say we got a little bit into Montana. We may have, but then we crossed back in Idaho and down into Wyoming, okay? And as we were driving, we ran into several really big wind farms. These are up high elevations fairly much. Wind was very constant. Those things were churning out the energy. Now, there were some places that farmers were underneath these things. You see how high they sit off the ground? The farmers underneath them. Now, there's no farming done there. That looks like desert almost under there. But there were farmers down there baling hay. So they were still using their land. They just couldn't use the base where the thing was, but they could use most of their land. They were getting rent from the power company. So it's a pretty good deal. And those things were whirring away. Now, some people don't like the noise. To me, it was a sound of money. Okay? Very good thing. Wind energy has been increasing in recent years. Manufacture of electricity by wind is happening. Another is called geothermal energy. That is energy from the earth. Now, there's no place here in the Southeast that I know of that uses this. Can't use it. The closest would be some of the places like Warm Springs, Georgia, and I'm not even sure there's enough heat there. Sure, there are warm springs that bubble up from the ground, but I don't think it's enough to power very much electrical generation. But places that are near volcanic rock, they can use that hot rock to heat water, make steam. Steam turns the turbines, manufacture electricity. Clean, straightforward. You just have to be very careful when you're drilling down in that volcanic rock that you don't cause a volcano eruption. Okay. Then they have the last one they mention here is solar energy. And this is a picture of a garage with, I bet you that's the south-facing roof of the garage. They just about totally covered with a solar panel. And that converts sunlight energy into electrical energy. That's what solar cells do. However, only about half the day is the sun shining. And on cloudy days, it's not shining very well. Rainy days, you're not going to get much at all. Okay? But it's still using cheap, available energy. Now, the solar cells themselves are not cheap, but the source of the energy, the sunlight, is free. Okay. And moving on from there, they talk another physics connection on wind energy, well worth a read there. And then physics on the job, wind turbine technician. If you want to get into a growing field, that is a growing field. Then we have the glossary, not very long glossary here. And then formulas. We've used just about every one of them. They list 4, but you know you can manipulate those around. There's actually 5 or 6 there. Don't worry about the ones with thetas in them, trig functions. Don't worry about those. Review questions, good thing to look at for conceptual purposes, but your review problems, that would be another good thing to do. The odd numbers of these are in the back of the book. So if you needed a few more problems to work on, there's some. Any of the odds 1 through 15. Now, this figure here is an applied concepts problem. You don't need to do this, but let's just sort of talk through it now. Another roller coaster problem. The highest point on this is 60 meters above the ground. Somehow you got your roller coaster up there. And at that point, they're saying you have 0 velocity. You're not pushing that cart, you're letting it roll from a rest. So what happens with it, it goes down and you can calculate the total mechanical energy here is mgh. So whatever the mass of that cart is with people in it, whatever that is, that multiplied by g, which is 9.8 meters per second squared, times 60 meters, that's your total kinetic potential energy here, which is your mechanical energy here. When it reaches the bottom here, all of that is kinetic energy. So convert that and see how fast you're going. You're going quite fast because 60 meters is way up there. That's 6-story building up, okay? But then, then you start climbing again. So at this point, you're losing your speed, but don't lose all of it because you're only going here, which is 20 meters up. So you still have 1/3 of your kinetic energy. Now, that's not 1/3 of your speed, but 1/3 of your energy is still kinetic energy. 2/3 is, no, I'm sorry, 1/3 of it is potential energy. 2/3 of it is kinetic energy. You come back down to the maximum speed again, and now you go up 30 meters. Now you slowed even more. You got half of the total energy you had here is now potential. Half of it is kinetic. Then you go here again, and you go up 40 meters. Well, you make it up there. Okay, here comes Mercy. Mercy me, we've got 100% attendance of those people who have been in the class from the beginning. So here we have it. Good deal. Way to go, Tim. Okay, so up here you've now 2/3 of your energy is potential, 1/3 is kinetic. And then you come back down and you're at maximum speed again, or very close to it. Okay. That's what this problem was dealing with. You can work it out if you want to. Not necessary. All right. Any questions? That's chapter 8. Once I shut down tonight, I will load your chapter 8 test. I went through and cleaned it up a little bit. I made it out last term, but it was kind of messy. So I cleaned it up a little bit. And so that I will be loading for you after class tonight. So watch for that then. Chapter 8 test. We'll move from chapter 8. We're not doing chapter 9. That's rotational motion. Not doing that. Or chapter 10, whatever that is. I missed 10 somewhere in there. That's simple machines. Okay. Chapter 11, we're not doing either. That's universal gravitational and satellite motion. Not doing that. It's all good stuff, but we just don't have time for it. The next thing that was called for in your course description, which is what we go by, is basic concepts of matter or something like that. And that's where we're going now. I can't get the thing to move. So now we'll end chapter 8 and move to chapter 12. There, nope, where is chapter 12? There it is. PowerPoint on chapter 12. Okay, here we go. Let's go from current slide and it says here screen clearing is stopped as the shared window closed. Okay, but now we're screen sharing again. Can you see chapter 12 matter? Yes or no? Yes, okay. I thought that was wrong, okay. So let me move. I don't know if you can see it. That's my toolbar. It just gets in the way. So let me get it out of the way down here. And so we're going to talk about matter. All right. First slide here. Well, how to get to the first slide. First slide here is on the next page. Before we get to that, so let's back up one. Let's go back to our whiteboard. Okay. Now let's get this bar out of the way. I don't know if you can see it, but it's definitely in the way. Okay. And all right. Let's hit some definitions. So I'll try to type these in quickly. Do all of you have books, or is somebody still without a book? Anyone without a book? Please let me know. Everybody got a book?
Yes.
Yes? Okay. Well, maybe I don't need to type these in. If you got your books open, I'll just read these definitions that are pretty important. So you need to know. First, matter. Matter is anything that occupies space and has mass. That's just about everything. Air occupies space, it has mass. Not a lot of mass, but it has it. Certainly solids occupy space, they have mass. Liquids, water I was drinking, occupies space, it has mass. Anything like that is mass, is matter. Energy is not matter. Energy doesn't occupy space, it doesn't have mass. It may depend on the mass, but it doesn't have mass. Okay? So matter is anything that occupies space and has mass. Now, we're going to be hitting a concept here that I call microscopic, macroscopic. Macroscopic is the big picture. Where we live, what we see, what we experience, that's macroscopic. Microscopic means what's happening on the very tiniest scale that you can go to. In fact, what we're going to be talking about is actually submicroscopic, smaller than you'll see with any microscope you'll ever be around. Okay? So, let's talk about these concepts. The first is the concept of an element. Now, an element, and this is on your page, goodness, I don't see the page number, 310. Okay? An element is a substance that cannot be separated into simpler substances. Now, an element is a macroscopic concept. Okay? I'm going to name a few elements. You're used to hearing them. Oxygen, hydrogen, nitrogen, iron, copper. Those are all elements. Okay? Those are materials that cannot be broken into any simpler substances. You cannot break iron into any smaller things that make up iron. Iron is iron. Oxygen is oxygen. Nitrogen is nitrogen. Hydrogen is hydrogen. Sodium, sodium, whatever. Now, again, macroscopic concept. Another macroscopic concept. And by the way, and this book I wish had a periodic table. It doesn't, that I've been able to find anyway. Okay, I've looked for it. I think every time I've taught the course, and I don't think it's in here. Oh wait. 628 or 643. Let's see if it's on any one of those pages. 628 or 643. No, they talk about the periodic table on page 628. 643. I think I've done all this before. That's the definition of the periodic table. No, the periodic table is not to be found in this text. Okay? But on the periodic table, there's a listing of something in the neighborhood of 100 elements. Most of them have a few more than that, maybe 108, 116, some number somewhere around 100. Not that many. That's all the elements we know in all of nature. It's not saying there may not be a few more out there somewhere, but it's all the ones we've either detected or at least hypothesized are there. Not that many, okay? And many of those are very rare. Some of them are radioactive and don't hang around but for a fraction of a second, but those are your elements. Everything else, look around you. Carbon dioxide I'm breathing out. Water I was drinking. Wood. The material this chair is made out of. Just about anything you can think of. Glass. Okay? Soil. Anything you can think of, those mostly are made up of compounds. A compound is a substance that contains two or more elements. Okay? Generally different elements, but occasionally the same one. Okay? So, I've named several. Sugar, water, carbon dioxide, ammonia, you name it, the odds are it's going to be a compound, not an element. There are thousands upon thousands, maybe even millions of compounds out there. Okay? A substance containing two or more elements. Those are macroscopic concepts. Now let's look at the microscopic concept. A molecule is a collection of atoms. So I want to start with atom. The book started with molecule. An atom is the simplest particle that an element can have. A single atom. You can have iron atoms, oxygen atoms, nitrogen atoms, hydrogen atoms, carbon atoms, magnesium atoms. Any element, the smallest unit that you can have of that is an atom. Okay? So that's a microscopic concept. Atoms refer to elements. Elements, the macroscopic, atoms, the microscopic. With compounds, macroscopic, the corresponding term is molecule. A molecule is the smallest particle, I don't like the way they say this, of an element that can exist in a free state and still retains, and that's where the wording is bad. Here's how I would say it. A molecule is the smallest particle that a compound can have and still retain its characteristics. Now, compounds or molecules are made up of two or more atoms, but to maintain the characteristic of that compound, that's going to be a molecule. Sure, you can force them apart. For instance, let's say carbon dioxide. That's carbon with two oxygens. Okay, carbon dioxide is the gas you breathe out when you breathe. Okay, and that's made from the carbon that your body has just metabolized from your sugars that you've eaten and carbohydrates that you've eaten. That's where the carbon comes from. The oxygen comes from the air, but also from those carbohydrates as well. Excuse me. So, but you can chemically break that carbon dioxide into carbon and oxygen. Okay? It won't be carbon dioxide anymore, though. To be carbon dioxide, it's going to be in that CO2 molecule. Anything you do to it that breaks that up, no longer carbon dioxide. So a molecule is the smallest particle that a compound can be in and still retain the characteristics of that compound. Now, here's where things get a little strange. I mentioned oxygen and nitrogen and hydrogen. Those are gases made up of atoms, all the same kinds of atoms, but for every one of those gases, there's actually two atoms that join together. So an atom of oxygen would be a single, but you don't ever find that. Most of the time you have O2, that's one molecule of oxygen. But it's made up of two atoms. The two atoms just both are oxygen atoms. So that oxygen atom is still oxygen, okay? But it never exists by itself. It always exists as a pair, a molecule of O2. So a molecule can be only one type of atom, so it can represent an element. But most of the time, molecules represent compounds because you have a lot more compounds than you do elements. Okay, so there they've hit their characteristics. Okay, now they throw some numbers here, and you'll see them in your book. Most simple molecules are about 3, now this is approximate, 3 times 10 to the minus 10th meter in diameter. Well, what is that? Let's picture a dime, okay? A dime. You know how thin a dime is. That's about 1 millimeter, which would be 10 to the minus 3 meters. If you were to slice that dime into, this is just rough, around 3,000 slices, okay? That thickness of the dime, slice it into 3,000 slices. I can't even imagine that. I can't think of any way you could do it. That would be the maximum diameter of most molecules. Incredibly small, microscopic, submicroscopic, okay? Now, let's talk sizes now, okay? That's sort of what we're doing. The hydrogen atom is the smallest atom. It has a diameter of about 6 times 10 to the minus 11 meters. That now you've sliced into 6. I'm having trouble even coming up with that. 3 times 10 to the minus, let me see, 7. That would be, you slice it into 30 or 300,000 slices on average. This is about 6 million slices. So it's incredibly small. Those aren't quite right, but there. The mass, 1.67 times 10 to the minus 27 kilograms. That's so incredibly tiny. So that's the smallest. The largest, one of the largest, heaviest atoms, uranium, is 3.96 times 10 to the minus 25th kilograms. So it's a little bit better than 200 times more massive than a hydrogen atom, sure, but it's still incredibly, incredibly small. Okay, now, so much for just general numbers. Let's go back to our slides, and this slide is actually a fairly good slide. There it is, chapter 12. Oops. Oh, that's not what I wanted. Yeah, it is. Right here. All right. Here is a water molecule. Well, oh, goodness gracious, why are you checking? Here is a water molecule. You have an oxygen atom here represented by the green ball and two hydrogen atoms represented by the blue balls. Remember, hydrogen is the smallest atom out there. Oxygen considerably bigger, okay, maybe even bigger than this indicates, but that's just representing a water molecule. Now you might say, why did they put the hydrogens off to the side like that? Well, that's how they come. Because oxygen atom likes to have 4 pairs of electrons around it in its outer shell. Here would be a pair that's not attached to a hydrogen. Over here would be another pair. And what these form is that forms an equilateral triangle this way, an equilateral triangle that way, equilateral triangle that way, every way an equilateral triangle. But these are unpaired, these are paired electrons here. The oxygen and hydrogen share a pair of electrons here and here. You don't need to know this, but that's why it's offset like that. Always is. Now, one of the ramifications of that makes water a very strong solvent. This side tends to be a little negative, this side tends to be a little positive. We call that a polar molecule because the hydrogens are congregated on one end and the oxygen is bulging on the other end. Oxygen tends to be negative, hydrogens tend to be positive. Why? Because they're sharing the one hydrogen electron with the oxygen, so a lot of times this hydrogen is a bare proton. Same thing with this one, so that's a positive charge. This has 2 pairs of electrons out here that tend to be negatively charged, okay? So that makes water a polar molecule, making it an excellent solvent. It will dissolve things. It dissolves sugars. It dissolves salt. It dissolves lots and lots of material. It won't dissolve a material that's not polar, like oil, grease, wax. Those things will not be, and that's why water beads up on a wax car, or it stands on, or oil stands on water because it's lighter than water. So there is an example of one molecule of water made up of 2 different atoms, 3 atoms, 2 of them are the same and 1 of them is different, okay? Here is the simplest sugar molecule you'll ever find. It's called glucose. Now, it's very similar to fructose and sucrose, okay? They just have a little bit different arrangements, but they're made the same. Here, your red balls are your carbons. Now, they don't have the balls in relative sizes. They made them all look the same size. That's not correct. They should be different sizes like you saw different sizes here. But they can't do it so much here. The red balls are carbon. The blue balls are hydrogen like they were here. And the green balls are oxygen like you see here. Okay? Now, notice that all the carbons are always connected to another carbon. Some of them to 2 carbons, the ones on the end just to 1 carbon. Okay? Every carbon is connected to at least 1 hydrogen. This one's connected to 2. This one's to 1, that one's to 1, that one's to 1, this one's to 1. So the only one of them is connected to 2. Every oxygen is also connected to a carbon. Every oxygen is connected to a carbon, but only 1 oxygen per carbon. Most of the oxygens are also connected to a hydrogen, okay? And there they all are, okay? Except for this one. This one is not connected to a hydrogen. Now what it has is called a double bond here with the carbon. Now here's a characteristic of these elements. Carbon has 4 unpaired electrons, so it likes to pair up with something else. Hydrogen has 1 unpaired electron, so that makes a pair right there, the pair right there. This carbon combines with one oxygen. Oxygen has two unpaired electrons. So there it connects one of them with a carbon here, the other one with a hydrogen there. Remember, hydrogen has one unpaired. The fourth carbon connects to another carbon. So look at the pairs that you have. Out of a carbon, you have 4 pairs sharing electrons with either a hydrogen, oxygen, or another carbon. This one has 4. 1, 2, 3, 4. 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 This one has 4. 1, 2. But a double bond here. That's 2, because oxygen has 2 unpaired electrons. Hydrogen has 4, paired with this, paired with that. So they share 2 pairs here. That's what gives it a double bond. Hydrogen, only 1 unpaired electron, so it only connects in 1 pair. 1 pair. Where is my cursor? Come on, here it is. 1 pair, 1 pair, 1 pair. So the hydrogen always only has 1 link, either to a carbon or to an oxygen. Okay. Count what we have. 1, 2, 3, 4, 5, 6 carbons, 12 hydrogens. 1, 2, 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 6 oxygens. 1 oxygen to every carbon. So 6 oxygen. So here is the chemical formula for glucose or sucrose or fructose. C6, 6 carbons, H12, 12 hydrogens, and 6 O6, 6 oxygens. Okay. Whereas water, H2O, 2 hydrogens, 1 oxygen. Okay. Again, these are just a spatial representation, not completely accurate, just so you can see them better, because these 4 bonds here would be equally scattered around this. It looks like these are closer and these are further apart, and nothing over here. These are a little more equally, but you have nothing on the back side. These are a little more, these are fairly close to being well represented. This one, these 2 are awfully close together. They wouldn't be there. And these 2, now these 2 have to be close, so these are a little bit distorted. Okay? Don't worry about that part. Just realize that's a molecule of sugar, simple sugar, made up of atoms of carbon, oxygen, and hydrogen. Okay. That's how matter is put together. Okay. How are we doing time-wise? Whoa, only 4 minutes. Okay. Here are some properties of these atomic particles. Okay. Now we're going smaller than an atom. Remember, an atom is as small as you can get to be an element, but an atom is made up of smaller particles. And these are on your page 311. And we've already talked a little bit about these. I haven't mentioned 2 of them, I've only mentioned 1. A proton is a single positive charge. A proton has pretty large mass, comparatively. It's a very tiny mass, but it's more massive than an electron. It has a fixed diameter. Again, really, really small. And it has a fixed charge, +1 charge. An electron, on the other hand, is incredibly tiny mass. About between 1,000th and 1/10,000th the mass of a proton. And protons are pretty small, okay? So this is very, very small. They've never been able to determine what the diameter of an electron is. It's way too small. But it has a full minus charge. Same amount of charge as this big old proton here, but it's just the opposite sign. Negative for electron, positive for proton. Positive proton, proton. Okay. Neutron. Now what the new NEU stands for is neutral, meaning no charge at all. And look at it. It's almost the same size as a proton, if anything, just a little bit bigger. Okay? Not much, just a little bit bigger. Okay? and look at its diameter. You can hardly tell them apart. They are basically the same size volume-wise. It's just the mass is ever so slightly greater in a neutron. But a neutron has absolutely no charge. Okay? So keep that in mind. Now, the protons and the neutrons live in the nucleus of an atom. Now look at that. All the mass pretty much, and all the volume pretty much, actual volume of the things, are packed into the nucleus of an atom, of any atom. Okay? Now, the electrons with very, very, very little mass and basically no measurable diameter, they fly around in space around that nucleus. But they define the outer limits of that atom. Okay? So what you saw back here, this is the electron cloud around the hydrogen. And it only has one electron, but it's floating around there. Somewhere in the center there is a single proton. One electron flying around here, mostly linked with the oxygen, but not always. Well, it is linked, but sometimes a pair of them float around. But that's what represents there. This oxygen has a nucleus in here with, let me see if I can remember, 6 protons and 6 neutrons, okay? In a very incredibly tiny little volume in here, but that's all the mass. These electrons, these 8 electrons that are flying around out here, have basically almost no mass at all. But they take up the space, the volume of that oxygen atom. Okay. They have no measurable diameter themselves, but they fly around and occupy the space around that. So most of everything is nothing but empty space. The space in between those electrons in that cloud. But you can never tell where the electron is because it has such a tiny volume you can't see it at all. You just know where it probably is. Okay. Now, how are we doing on? Oh, we just ran over. All right. So we're starting next week on the top of page 312. Now, we didn't get anywhere along here for any problems. So all your problems are still in chapter 8, and you'll be getting your test hopefully in the next few hours. I'll be able to get that test loaded. Okay? Any questions? Either chapter 8 or chapter 12 so far.
You said on 8.4 it was 1 through 14 on what page?
Any of the odds 1 through, I think it was 13. Okay, wait. Oh, I'm sorry, I'm in the wrong chapter. Let me, before I do anything else, get a marker in place. Okay, now, go back to chapter 8. Okay. Just past chapter 8. There we go. And 8.4 you said?
Mm-hmm.
Okay, 8.4, 1 through 13 on page 224. Any of the odds 1 through 13 on page 224.
Okay, thank you.
Good deal. And you'll be getting the test. I want to say soon. I don't know how soon it'll be. I've got to get everything shut down. I've got to get your attendance marked today, and I've got to take care of close out the screencast-o-matic. I got a few things to take care of, and then I'll try to get your. I've got to also send out announcements for my next Zoom class. Okay. But once I get that done, then I'll get your test loaded. It'll be on Blackboard under Messages. Okay? Good deal. Any last thoughts, questions, parting shots? Okay, I'm going to stop the sharing. I don't like to share anymore. I'll end the meeting. And if there's no more comments, we're out of here. Take care. Have a good, safe weekend. Okay? We'll see you next week.